All right, should be recording now, so it's over to you guys.
All right. Then I guess I will start. I believe William has control of the screen sharing, so I'll just tell him when to go to the next slide. All right. Hello, everybody. We are Group 12. I'll allow everybody to introduce themselves, but we are presenting BioBox, the autonomous microbioreactor for the UF Biofoundry. My name is Benjamin Leach. If everybody else wants to introduce themselves.
I'm Harrison Klein.
Will Hartzell.
Joshua Copeland.
Noah Robertson.
Jacob Henderson.
Sorry. Al Pastor.
All right, so now we're going to kind of go over our presentation outline. Our outline is kind of split up into 6 different areas. First, we're going to go over our Hedgehog concept and what makes our design unique. Then we're going to go into our product overview, and then we're going to take a little bit of time and talk about our design subsystems and what's unique about each of our subsystem, talk about some of the analyses that we did for every subsystem, the TRLs for every subsystem, a cost analysis of our overall design and each of the subsystems, and then just go over some additional details and overall why BioBox is a strong solution for the customer needs and problem we've addressed. So to go over our Hedgehog concept, BioBox's driving concept is to provide the most user-friendly handling capabilities by minimizing costs associated with system errors and confusion. So in our product overview, we kind of hit some of the main points that are addressed by the customer needs and overall just with the design of our concept. So first, we have a total weight of 415 pounds. And as you'll see later on in the design, we include some water tank coolers, and in that 415 pounds, we incorporated the 2 water tanks at full capacity to get that weight. We also have full dimensions of 43 inches by 25.5 inches tall by 35.5 inches wide, with a maximum power consumption with every single motorized or electronic component operating. We consume 1,527 watts. And we also include a modular frame design, which allows for the inclusion of additional subsystems and additional systems to be put into place once this design is actually created and put into field. We also offer dual chambers for gas and temperature controls, which allows us to operate 2 completely separate chambers of environmental and gas control. We also offer 3 axes liquid handling, allowing for us to move liquid in any of the 3 XYZ axes, as you'll see in our subframe. And we also offer reusable disposable syringe tips, which allows for us to offer syringe tips which offer a multitude of not only volume capabilities, but also the ability to handle liquid without cross-contamination. So next, we're going to go into each of our subsystems. Specifically, we have 7 subsystems, which include a frame, a liquid handling movement, a liquid handler, a liquid handling movement, light emission monitoring, temperature control, gas control, and a shaker. Harrison, you want to take frame?
Sure. So I'll start with the frame. Obviously, as you all can see, our frame is multifunctional. In the case of the 8020, we are able to attach rails to that for the liquid handling subsystem to move on. That's going to take care of both of our X and our Y directions. And additionally, it'll allow for the attachment of the axis or the component that allows for the movement in the Z axis. As most of you know, we all had experience with 8020 heavily in the DML course. It's a very inexpensive and lightweight, material that conforms to quite a few of the customer needs that were addressed initially. And then once again, one of the customer needs was pertaining to the heat transfer and the temperature ranges that were allowable on the exterior and the interior of the system. Once again, affording to the user friendliness, the box is open on all of the sides, which later on you will see allows for the laboratory technician to access any of the components on the inside for repair or access any of the cell cultures to change out for different experiments. Once again, like I just said, 80/20, very easy to use. It can be put together and taken apart in seconds with the use of nothing other than simple hand tools such as screwdrivers and Allen wrenches. So that's going to afford us a much shorter assembly time for the frame. And then furthermore, the customer needs that we're addressing with this system are needs 1, 11, 17, and 20, which are that it has to fit inside a research facility on a benchtop, as Benji noted prior. This does have a relatively small, in the grand scheme of things, overall size and its footprint. So it's going to conform to the try to have requirement of having a 0.61 meter height by 1.22 meter length and 0.61 meter depth. It's going to very well easily conform to that, fitting inside those requirements and fitting atop any of the normal bench tops. Once again, the overall cost of the system was not to exceed $10,000. This did not cost any more than, I believe, about $250. So we kept that price pretty low in order to allow for the other subsystems with more expensive components to take on a larger portion of that budget. In terms of the heat transfer, we know that the materials that we used had to allow for a exterior surface temperature to not exceed 55 degrees Celsius. And on the interior of the subsystem, there's a temperature range of 4 degrees to 70 degrees Celsius. So we had to account for all of those temperatures when we were designing insulation and using materials that we were going to actually seal the frame of the box together. You could advance to the next slide, that'd be great. So speaking to customer needs 17 and 20, as you can see on the right, that calculation was performed to determine what the rate or what the range of heat transfer would be to allow for that temperature range, obviously between 4 and 55 and 55 and 70. Once again, we knew that we were going to need insulation to allow for this. So you can see on the calculation on the left is the calculation for the insulation used, which came out to 0.0889 meters, which is just in the realm of about 2 and 2.5 inches. You can advance, Will. So moving on to the technology readiness levels, obviously 80/20 and the fasteners are off-the-shelf parts, so they are going to have a higher TRL than, say, a sheet metal component, which was going to be manufactured at some point later on by a third-party manufacturer. That's going to have a much lower TRL as it is not a full-fledged design. It is going to be in production, and it's not fully tested in the field. So as the lowest TRL is a 3 of the sheet metal, the TRL of the entire frame subsystem will be afforded a level of 3.
Okay, so now to go over our liquid handling subsystem. The liquid handling subsystem is the subsystem that allows us to transfer liquid between micro plates and conical cylinders, like 20 milliliter conical cylinders and 50 milliliter conical cylinders. And one of the unique things that we use in our design is the concept of disposable tips. And what those disposable tips do is they allow us to eliminate cross-contamination of cell cultures. So we are able to move any type of cell culture from one location to another and then dispose of the tip in our waste container. And essentially what that does is it allows us to eliminate the possibilities for cross-contamination and also eliminate the need to clean out our syringe in between individual uses. So the way that we operate our syringe pipette system is through a lead type motor, a through type lead screw motor. And basically what that does is it allows us to operate the plunger, which you can see in the figure, without the actual need for moving the motor itself, which would occur in a normal servo type motor. And what that allows us to do is it allows us to have a static system, which involves only the movement in the Z direction to operate at different heights, as well as remaining stagnant within that system. So in this subsystem, we address customer needs 7, 11, 13, 25, 33, and 34, specifically relating to the emergency shutoff, which we operate by ensuring that no excessive amount of force is applied to our liquid handling subsystem during movement. We keep costs low in this system by only operating under one motor using basic commercially available syringes and pipette tips, as well as a basic programming with very simple fluid addition and subtraction. We meet the customer needs flow rate, and we also have a minimum maximum volume that meets the 20 milliliter customer needs. So in that in that concept, some of the important things that we cover are first the cost calculation. Our liquid handling subsystem is at a total cost of $161.97, and that's significant because it again allows us to put more money into other subsystems, specifically some of the more cost inhibitive subsystems such as our heat exchanger and our gas gas monitoring or our gas displacement subsystem. And one of the unique things about our subsystem specifically is the way that we operate the disposable pipette tips, specifically through a snap-on fit. So our pipette tips are snapped in to the syringe itself through a vertically in the Z direction applied force, which we've calculated to be just shy of 3 pounds, which is completely operational under the stresses of our liquid handling movement subsystem. And then we are able to engage through that force and disengage through a shear force in the Y direction, which is a little less than 1.5 pounds. So overall, we're able to very easily remove and add on additional pipette tips. So overall, now we can talk about the technology readiness levels of the liquid handling subsystem. The concept has achieved a proper level of analytic and experimental analysis. However, it has not been tested yet in the laboratory, so we afforded it a technology readiness level of 3.
So the liquid movement subsystem. We selected inexpensive and lightweight materials that allow for modularity and synergy between the frame and liquid handler subsystems because the liquid movement is going to be attached directly to the frame and just allow for synergy. We have an automatic triple axis motion control, which includes an emergency shutoff if necessary. We use 80/20 for the framing of the liquid movement, which allows for modularity. And the customer needs addressed here are the cost, which can't exceed 10,000, which here is around less than 1,000 per subsystem. The need to number 25, capable of automated liquid handling that permits new fluid subtraction from each well/tube. We ensured that the motors were fast enough. And the try to have need number 3, process of 384 well plate in 6.5 minute window. Same thing as number 25. We ensured that the motors were quick enough to get from point A to point B and go up and down. Perfect. So we had the cost calculation, which this subsystem rounds out to about $566. The XYZ, we ensured that the motors had some sort of force or motion in every XYZ plane, and the speed of each, it takes about 5 seconds to traverse the entire distance at going at 25 RPM, which these motors can go up to 750 RPMs, but we're going at a slow speed to ensure accuracy. And then a 384 well plate. All right, perfect. That's good. You can go next. Same as the other subsystems, we have a TRL of 3 because certain custom parts are used in manufacturing. Even though the liquid movement subassembly is made up of nearly 75% off-the-shelf parts, which yield a higher TRL, you have to choose the lower TRLs that would make up the subsystem.
The next subsystem that we'll go over is the light emission monitoring system, or what we call the LEM. So the 2 main components of the LEM include the measurement devices and the lighting source. The measurement devices, which are designed referring back to customer needs statement 28 and 29, include a photomultiplier and a monochromator, and they are attached to the liquid handling subsystem. Because of this, we are able to precisely position the devices over specific well plates where the fluorescent intensity and optical density can be measured simultaneously. We chose to use the photomultipliers and the monochromator because this is what we found to be typically used in fluorescent plate readers. The lighting source features 18 red and blue LEDs that are attached to a bracket located directly over the well plates. You can see this model of the bracket and the lights to the right. The red LEDs emit a wavelength of about 630 nanometers. This is about 10 nanometers less than the one listed in customer need 30. However, it will still be good enough for optimal culture growth during experimentation. We added blue LEDs that have a wavelength of 450 nanometers, and this is to help with sanitation and to prevent contamination between experiment trials. Next slide. So one of the major calculations we use in our design was finding the intensity. This was found by just dividing the power of the lights over the incident area of a well plate. The manufacturers of the LEDs only listed the maximum light output, so we just had to divide that by the typical efficiency of an LED to get the power. The subsystem was one of our more expensive sections, despite having the least amount of parts. Most of the cost came from the $825 monochromator and the $160 photomultiplier. Next slide. So in terms of technological readiness, we feel that it's only at a level 2. We have a concept, but I think it requires a bit more research and optimization and better application, since this was an area where we had very little experience in. As for each component individually, I think they have a moderate technological readiness. We just need hands-on testing.
All right, so that brings us to the temperature control subsystem. So the temperature control subsystem features a dual chamber control for the evolver in the primary chamber. This is beneficial if the researcher would like to have 2 different environment temperatures. The heating element that's going to heat the water for the closed loop system is going to come from a water cooler tower you might find in an office workspace. And has a temperature range of 4 degrees Celsius and up to 70 degrees Celsius, which fits the customer needs. So if you look at the picture on the left, you can see a bunch of fans attached to the heat exchangers. These fans create forced convection environment to maximize the heat transfer. Without these fans, it would take a long time for our system to heat up. It actually takes 144 seconds to heat our system from 4 degrees Celsius to 70 degrees Celsius, which is just under 2.5 minutes. Some customer needs this subsystem addressed is the power consumption, has an emergency shutoff, the operational lifetime. It doesn't have a high cost. It conforms to the temperature range and has uniform heating. All right, so the first analysis, we're going to look at the temperature range analysis to define by customer need 20. So we found the heat flux, the Reynolds number to determine flow, the average Nusselt number. From that, we could find the average heat transfer coefficient. We could use the log mean temperature, and then plugging that back into the heat flux equation at the bottom, we can find the max temperature achieved by the subsystem. Conversely, if we look at the minimum temperature, we found that our system can only go up to 4.8 degrees Celsius. And this is due to a problem that we didn't first think of. Actually, Dr. Traum mentioned it during our poster symposium, that motors and all these systems within the BioBox are going to generate a decent amount of heat. So there's clearly a problem. So for our final design report, we're looking at a solution. It's going to be a Peltier element to help remove that little bit of heat from the system to reach the full customer needs temperature range. The next analysis is going to be the time it takes to heat from the lowest to the highest temperatures defined by the customer. So we found the Reynolds number, the Prandtl number, the Nusselt number, and that we find the average heat transfer or convective heat transfer coefficient. Using a lumped capacitance method, we can find the time it takes to heat the system. And like I mentioned before, it takes 144 seconds or just under 2.5 minutes to heat the system. And this calculation is with the fans attached. That was pictured previously. Without the fans, it would take somewhere on an order of hours instead of minutes, which is not what the customer would want. The overall technology readiness level of the temperature control system we'd find to be level 2. It's mainly composed of a bunch of over-the-shelf parts, such as a fan, heat exchanger, and a pump. And these will get a level 6 because we've seen them work in a similar environment, just not ours. However, the heating element is going to be a modified over-the-shelf part. And due to the modifications, we don't know if it'll work exactly the way we want. So right now, the concept is just formulated, and we have no experimental data to see if it'll actually work.
So for the gas control system, the parts that we thought were different than what would be the normal setup for it, where we have a dual chamber gas control setup and we have an exhaust pump to relieve the unwanted gases. So how that works is for each of the 5 gases, we have 2 hoses to insert the gases into either the main chamber or into the evolver. And the main chamber is where we're having the unfavorable conditions, and the evolver is where we're housing the favorable conditions. And we have a valve for each of these connections in order to direct these gases into where they're supposed to go for specific testing. And the customer needs addressed in this are 4, 7, 10, 16, 26, and 27. And yeah, thank you. And so we have these 2 analyses for the gas insertion time and the gas removal time. So the flow rate for the gas insertion is dependent on the gases. And the equation here shows that the flow rate would be 964 times the flow constant of the valve, which was given from the website that the valve was being sold from. It is an OTS part. Multiplied by the square root of the pressure drop times the inlet pressure plus the outlet pressure divided by the specific gravity of the specific gas, and then the absolute temperature of that gas. So the coefficient for this specific gas valve was 645, and the pressure drop was 1.3, while the inlet pressure was 2.0 and the outlet pressure was 0.7. So then we were able to find the time that it would take to fill the chamber with the gas by dividing the volume by the volumetric flow rate. And the total volume of our primary chamber was 11,474 inches cubed. And for our evolver, it was 1,326 inches cubed. So below we have the results for nitrogen, oxygen, carbon dioxide, methane, and hydrogen, and exactly how long that they would take to fill both of the chambers. As you see, for example, nitrogen has a specific gravity of 0.97 and an absolute temperature of 139.6. So the flow rate came out to be 482.6 inches cubed per second. And the time to fill the primary chamber would take about 23.78 seconds. And to fill the evolver, it would take about 2.75 seconds. And while the insertion time, the flow rate was dependent on the specific gases. For the exhaust pump system, which is how we're relieving the chambers of the gases in between tests, because initially we had run into an issue in the design meeting where we were mixing gases and it could potentially become dangerous. So we added this exhaust system to remove the gases in between testing. And for this pump, it came with the flow rate provided by the OTS website, and it came to 0.6 CFM for the flow rate, which was converted to 17.28 inches cubed per second. And then plugging that in for both the primary chamber and the evolver, estimated that the primary chamber would take about 664 seconds to remove the gas from the chamber and about 76.74 seconds to remove the gas from the evolver. And then due to the fact that these are all OTS parts that have been used and proven in other situations, but not tested in our specific environment, the overall system had a technology readiness level of 6.
So here is our shaker subsystem. It features 2 NEMA 8 stepper motors attached to a linear DC servo linear actuator. It has the capabilities of moving in linear, orbital, and double orbital motions, which are optimal for in our situation for specific bacterial strains require specific shaking patterns for optimal growth. It has capabilities where the gears can be modified to change the shaking patterns and adjustments. And the customer needs addressed here were to accommodate for culture plates up to 384 cells, and for conical tubes up to 50 milliliters. And of course, customer need 31 to have all three linear, orbital, and double orbital shaking patterns. And from the customer needs addressed, it was essential that the base of the shaker system was greater than of the well plate to be able to accommodate for the size, and that for the motor assemblies used for the shaking patterns, the volume of the base was able to fit inside of there. And the double orbital pattern was inspired by Clayton L. Wagner, who patented this mechanism, where as you can see in the photo in the middle, how it has connecting rods attached to the gears from the center of the motor to the end, and they meet at a middle plate. And as it spins, the gears must be counter-rotating in the same direction in order to achieve this pattern. And then with variation and the distance between the gearing, it can change how the motion pattern affects it. And it has linear displacement speed of about 3.1 meters per second. And overall, the TRL rating was at a level 2. While most of it contains OTS parts such as the motors, other parts such as the base, connecting rods, and gearing would have to be self-manufactured. So it would give an overall rating of a level 2.
So now we'll go into our overall cost analysis for the entire BioBox. So we've added our total cost for the entire machine is $9,180.21. And that comes down from multiple factors. First, we'll look into OTS parts, which is a majority of our cost for this system since we decided to go with an OTS heavy design, which is $6,592.47. With that, we also have a little over $1,500 for raw materials, such as the sheet metal used in our frame subsystem and the plating used for our motor mounts, as well as a little under $200 for our shipping, $475.08 for manufacturing, as well as $340.44 for assembly. So to kind of just roughly go over some of our customer needs mapping, we have gone into every single customer need and basically mapped out a quantitative metric for it, such as you can see with the bench top size, the total weight of it, or the power requirements, what the total wattage required for under worst case scenario conditions is, and we've mapped that out into each individual subsystem, and that was some of the stuff that we just went over in each of our subsystem designs, overall to ensure that every subsystem ensured that every customer need was met and that every customer need was met within each subsystem. Harris, you want to take this one?
Obviously, going forward, moving from EML4501 to 4502, every group is striving to be that group that's selected to have their design move forward to the Mech Design 2 course with Professor Nimi. As stated in our Hedgehog concept, we feel we have the most user-friendly system that will hit the per se market. Obviously, that comes down to a lot of factors. The UI that will be developed is going to be very user-friendly, that you can see on the exterior touchscreen as in the SolidWorks. The ability for the lab technicians to use and operate this machine is very easy. Like you've seen in the SolidWorks figures, there's plenty of ways they can reach in, grab cell cultures, grab well plates. Everything fits, everything has a place. It's not cluttered inside at all, and there's plenty of room for them to work. like I spoke to in my frame subsystem slides, and everyone else has spoken to in their subsystems, as we do start off with a 80-20 modular system for the base, all the other components can very easily be attached and disassembled or assembled, whether it's for repair, cleaning, any aspect that needs to be hit on for that. It's very simple for a technician or a repair person to conduct anything they need to do. And then once again, like we spoke to in our Hedgehog concept, we noted that there's a lot of issues with cross-contamination and other factors that might skew data in experiments that involve cell cultures. We feel that our design here will do everything in its power and can do everything in its power to alleviate a lot of those issues that have been seen in prior experiments in this field. And obviously just wanted to give everyone a nice thank you. Obviously all the engineers that are coming from Cummins and Northrop that are here today, we do understand you guys have a very busy schedule. We do appreciate you took the time out of your day to come and sit in on not only our meetings, but the other, I believe 18 or 17 or 18 other groups that are in this course. Dr. Traum, we just want to give you a big thanks to spearheading this course this semester. As it's been a very interesting adjustment for us, we can understand how difficult it's been for you to teach a course like this that is very heavy on group work, that is very heavy on group meetings in this new environment, and then all the other MAE faculty that are here. I'm not sure if there are any, but we do appreciate all you guys that have popped into the other symposiums and our poster presentation this past Monday. We appreciate the comments from not only within our department, but the EE department as well. And then to all the teaching assistants, we do appreciate all your comments and all your help throughout everything, especially Lauren. You were our guide this semester. You helped us out immensely on a lot of the issues we ran into. So just want to thank all of you guys for everything this semester. It's been quite an interesting experience, but I can say this is one of the greatest experiences that I've had so far at UF.
All right.
So questions?
Yeah, thank you for the presentation. Are there questions from our panel?
So I'll maybe pick on a technical thing that jumped out at me. On your gas handling slide, you had a chart with absolute temperatures of gases, and I see. I'm not sure what scale you're using there. I assume since you're using English units that those are Rankine temperatures, but I see hydrogen at 36.8 and oxygen at 163. Those seem very, very cold.
Yeah, here we went at the boiling temperature for each and then converted it to Rankine. But if you think that looks off, I can definitely go back and check and reevaluate for the time for those specific ones.
I'm pretty sure those are at least in the ballpark for boiling. I just wonder why we're looking at temperatures quite that cold. I don't think we're handling any gases that are I mean, we're not doing anything with liquid nitrogen or liquid oxygen, I don't believe. I hope not.
Right. So just to ask you for moving forward, what would you suggest? Because what I went for this was when I went and found the equation, I had looked at it and it had told me to find the absolute temperature. And at first I wasn't 100% sure if I was looking at the temperature of the overall system or if I was finding the absolute temperature of where exactly it would become a gas. So I decided to go for the calculation with where it boiled as a certain temperature. Would you suggest to go above the boiling point, or where would you suggest for me to choose the proper temperature in order to find that moving forward when submitting the final design report?
Well, not being a thermal guy, I'm going to kind of defer to Dr. Traum on this one, but
Okay.
my sense is that it's the temperature the gases are at when they're being passed through the system.
Okay, well, thank you very much for pointing that out. I'll definitely go back over that and make sure that that's correct going forward.
Yeah, just as a quick maybe thermo add-on, if you're at the boiling temperature of the gases, they're actually more like vapors than gases, right? So they're not going to behave following ideal gas law. They're going to behave more like two-component liquid vapor mixtures. So yeah, probably stay far away from that temperature.
Okay, great. Thank you very much for the comment.
So I've got two questions here. 415 pounds.
Thanks, Sean. I was going to drive that too. Yes.
Right. That was the first thing. Like, it jumped at me. My video was off, so you guys can't see my facial expressions, but I think my jaw actually hit my desk. One, can a lab bench support that weight? A standard laboratory workbench, how much weight can that handle?
Yeah, so when we were doing some of our analyses, we found some pretty standard low quality lab benches, and that we kind of use that as our basis. And even the kind of cheaper, lower quality lab benches were still supporting weights upwards of 2,000 pounds. Just, typical laboratory benches that you would find in like a high school laboratory. So we felt very comfortable being, at least under 500 pounds, that we were at a factor safety of 4. And a big part of that 415 pounds was the 2 water tanks being filled at their absolute maximum level. So the key component of that weight, while yes, we did understand it was heavy, we made sure that every individual subsystem was still weighing, far below that 450, at the heaviest subsystem, which was the heat exchanger subsystem. We were still in the range between 60 and 70 pounds for that subsystem, which was important to us because we didn't want to have any non-disassemblable component weighing more than that, so that in the event that this product did have to be moved and actually transported from one location to another, that it would be without, impossible. Because 415 pounds is certainly outside of our weight range and definitely challenging to move, but every disassemblable subsystem during the process of transportation definitely weighs within our allowable movement weight.
How much?
So you're anticipating somebody doing substantial disassembly of this to move it around?
No, so we don't anticipate anybody doing substantial disassembly. Sorry, my throat is not good today. The kind of higher level of disassembly that we anticipate for moving around. Will, if you could go back to the primary picture of our heat exchanger right there. Oop, just passed it. So that our heat exchanger subsystem is the largest amount of disassembly that we would anticipate for this product. And basically what that encompasses is actually just disconnecting the copper tubing. So those 2 heat exchangers are actually inside of the primary chamber. And then all of the condensers and water tanks are outside of that primary chamber. So in order to move this system, we anticipate that we're going to be disconnecting the 2 systems from each other and then moving them separately, with individual components on the inside being able to be taken out. But overall, we're only anticipating having to disassemble the entire structure in an order of about 3.5 minutes.
And speaking of even further more to what Benji said, obviously we accounted for the full water tanks. Obviously water is quite heavy. I believe it comes out to about 3 pounds per gallon. I don't off the top of my head remember the exact capacity or the volumetric capacity of those 2 tanks, but that does take into effect quite a substantial amount of liquid weight, which would not be put into the system until it was on the benchtop. Like Benji said, and like was spoken to initially in the customer needs and by the Biofoundry members, this needed to be able to be set up and moved by 1 to 2 people. We also don't want to, incur any back strain issues with any lab technicians. So like you said, large weight like that would not be lifted off the floor, off a cart, up onto a standard lab bench. Like Benji said, it would be taken up in portions. And he said that none of those are going to exceed more than about 60 to 70 pounds, which is well within the range for 1 to 2 people to lift, depending on their size and strength.
You just said you don't know the exact number for the volumetric. size of those tanks?
Off of the
No,
top
I
of my head, I don't. I don't know if anyone that can speak to that. I just don't remember off the top of my head.
Those are both 14-gallon tanks, and so that came out to about 233 pounds of water when full. So that 415 pounds weight actually includes 233 pounds of water. So in an environment where those were emptied and then you would be transporting the liquid, you would be getting substantially lower total weights of, about 182 pounds. Or yeah, is that math right? Quick math.
I guess follow another question I had. When you were doing the calculations for the external temperature of this, how were you accounting for conduction through your aluminum 8020 to your outer surface?
So if you go all the way back, Will, to the initial where you can see all the components of the frame and the insulation and the outer shell. In heat transfer, when we were, tasked with taking under an analysis such as this, we would set up a resistor network and take into account all of the different components. So in this case, it would then, it would be the aluminum outer shell, it would be the insulation, and then it would be the 8020 material. So that was set up using a resistor network to take into effect.
So I didn't have this picture when I couldn't remember this picture from when I had seen it. The 8020 is not contacting the outer shell; it is contacting the insulation.
Yeah, that's
cool.
correct.
No,
So,
you guys are good then.
Okay, yeah.
Disregard that question.
No worries.
I have a question. So one of the customer needs was to be able to achieve like a closed loop control of the environment. So I was just wondering with like the gas system, how you'd be able to measure like the composition of the gas that you've put in and be able to reevaluate and add or remove to keep the environmental system constant.
Sure. Oh man, my voice will progressively get worse as this goes on, so I'm trying my best. But so what we initially anticipated was incorporating some type of sensor, and that was something that was actually addressed in the research symposium a few days ago, and we were looking into solutions for it. But we were basically planning on putting some type of sensor on the interior frame to basically just determine the gas composition of both the evolver and the primary chamber, so that we could determine how to remove in closed loop control gas with the pumps and efficiently add each of the individual gases as well.
Okay, thank you.
All right, so we're actually several minutes over, and we have another group that's set to go at 9:45. So let me just wrap it there. Want to thank you guys, group 12, for sharing your presentation with us. Did an excellent job. We appreciate all of the creativity and the calculations and the insight. So we'll thank you. And for the panel, let me drop into, well, let me stop recording first.